Hello my viewers, welcome once more to my channel. In this particular lecture, I'll be talking about linear momentum and collision. But first and foremost, we're going to look at linear momentum first. What is linear momentum? If you have an object that has mass m moving with a velocity v, that object will have linear momentum as the product of its mass and velocity. So assuming we identify the linear momentum of a particle by P, and m is the mass, v is the velocity, then mathematically linear momentum P is equivalent to m times v. Of course, the SI unit for mass is kilogram, the SI unit of velocity is meter per second, so that gives us a clear SI unit of linear momentum as kilogram meter per second. Of course, linear momentum is a vector quantity and it acts in the direction of the object's velocity. Linear momentum is related to force. How is linear momentum related to force? So that's what we'll be looking at now. So, like I said earlier, the linear momentum of any object acts in the direction of the velocity of that object. Now, if linear momentum is acting in the direction that the velocity is acting, it implies that for you to change, for the momentum to change direction, or for the momentum to increase or decrease, there has to be a relation with the velocity. What I mean is this: for the momentum to change, the velocity must change. So for the momentum to change direction, for the momentum to increase or the momentum to decrease, the velocity must be impacted upon. So either the velocity will reduce or it will increase. And how can that happen? It means an external force must be applied to that object. This can be more expressed by Newton's second law of motion. Of course, in terms of momentum, that law tells us that the rate of change of momentum of an object is equal or equivalent to the total force applied to it. So in terms of momentum, this is Newton's second law, which I just quoted. Force, total force is equivalent to the change in momentum. Change in momentum is expressed as this. This entity implies how the momentum changes with time, and this is the total force. But we know initially that P is what equal to product of mass and velocity, which is mv. So it means a change in momentum, like I said, will result in a change in velocity. So the mass is always constant. So change in momentum delta P will be equal to, since mass is constant, we say m, but the velocity changes, so we say delta v. So fixing this expression back into this equation, we have that the total force will be equal to mass times change in velocity all over change in time. But then from kinematics, change in velocity is equal to acceleration. That's the rate of change of velocity is equivalent to acceleration. So delta v over delta t is a, which is acceleration. So we can then say that the total force is equal to mass times acceleration. This expression here is a mathematical representation of Newton's second law of motion, which we have obtained using the concept of momentum. So you see that the rate at which momentum changes, the rate at which the momentum of an object changes, is equivalent to the total force acting on that object. So let's move on of conservation of linear momentum. That's the next step to take. What does this law tell us? The law of conservation of linear momentum states that for an isolated system of particles, the total momentum is constant. What do we mean by system? When we say an isolated system of particles, what does that word system imply? It's just telling us about the collection of objects within a particular surrounding that are interacting with each other. So if you have, let's say, let's just use a box for example. If you have, or let's use a room. If you have a room, you have some objects that are interacting with themselves in that closed room. You can call that room a system. You can regard that room as a system. But it's a collection of objects within a particular surrounding, and those objects they are interacting with each other. Then when you say an isolated system, when you isolate, let's say you have two boys, two kids somewhere. If you decide to isolate the two kids, it means that they are no longer interacting with themselves. So one kid is alone, the other kid is alone, interacting separately, maybe with some other kids. So in that case, they are isolated. The only force that they will experience will be the force that they are interacting with individually. So in the case of an isolated system here, we are talking about objects that are interacting with themselves and they experience only forces within the system, meaning there are no external forces. Assuming I have, let's say this is a box, for example. We have objects, let's call this an object, we call this an object, we call this an object. They are interacting with each other. Okay, so the forces that these objects experience will be the forces that are existing within this system, but not from outside. So they are not interacting with any object from the outside environment. They are just experiencing only forces within this system. So that's what we mean by an isolated system. Okay, so let's move on. Now let's talk about collision a bit. We'll elaborate on it later on, because you can't actually talk about the law of conservation of linear momentum without saying something about collision. What is collision? I have an object. Let's call this object A. This is an object A. We have another object B. This is object B. If you check A and B, they are not in contact. They are not in contact. So we can say before contact. Then if you have A and B now that are now in contact, this is object B, this is object A. They are now in contact. These two objects are interacting with each other. B is exerting a force on A is also exerting a force on B. So with this concept, with this idea, we can define collision as the interaction of two or more objects exerting forces on each other or one another. If there are more than two, we say each other. There are two, we just say one another. Now, taking these above concepts into consideration, we can now state the law of conservation of linear momentum. In a system of collision, the total momentum before collision is equal to the total momentum after collision. So this is a case before collision. This is a case after collision. Okay. What you are saying is that the total momentum that these two objects will have before collision will be equal to the total momentum that they will still possess after collision. So in other words, the momentum is conserved. The implication is that as far as this system is isolated, that the objects they are just experiencing only the forces they exert on themselves, then the momentum will always be constant. That is what this assertion implies. Let's move on and see what we have. Now, let's express the law of conservation of linear momentum mathematically. Assuming we have two particles that are interacting with themselves in an isolated system, let one of the particles have mass m1. Let the other particle have mass m2. If the first particle has initial and final velocities v1i and v1f, so that's for the first particle, the initial velocity is v1i and the final velocity is v1f. For the second particle, the initial velocity is v2i, so second particle v2i, the I indicates initial velocity, the 2, the subscript there indicates the second particle. So we have v2f. If we want to apply the law of conservation of linear momentum to these two objects, we will say that the momentum before collision, which is this is before, and this is after collision. So the momentum before collision for the first object will be m1. For the first object will be m1 v1i, while for the second object the initial momentum is m2 v2i. So that's why we have this. So we are summing the initial momentum of each of the objects, object 1 and object 2. We equate it to their final momentum, the sum of their final momentum. For the first object, the final momentum is expressed as this, m1 v1f plus m2 v2f. Some textbooks will use u to represent initial velocity and then v to represent final velocity, whichever notation you want to use. The most important thing is understanding the concept. So applying the law of conservation of linear momentum, we say initial momentum before collision is equal to final momentum after collision. So we use P1i to represent the momentum, the initial momentum of the first object, P2i to represent the momentum of the second object, while P1f is the final momentum of the first object, P2f is the final momentum of the second object. So this equation, having this equation with you, you can actually calculate any of the lost quantity, as in any of the unknown quantity. Let me use the word unknown. So if you're given some other quantities in this equation, you can always use them to find the unknown quantity. So when we say impulse of a force, impulse of a force is a term that's quite related to the linear momentum of an object. I will define the impulse of a force as the product of the force and time for which the force acts. So if an object is experiencing a force the force will act for a period of time. The time for which that force acts on the object is what we refer to as the impulse. So it's the product of force and time in simple terms. So if we use J to represent impulse, F is force and T is time, then it implies that impulse of a force is F times T. Just say F times T. F is force, T is time. SI unit for force is Newton, SI unit for time is seconds. But we know that 1 Newton is equivalent to 1 kilogram meter per second square. So if you combine these two, the impulse is seen to have the same SI unit of momentum, has the same SI unit as that of momentum, which is kilogram meter per second. Some few examples. Let's look at some few examples demonstrating what we have learned. In this first example, we have that a truck has mass 90 kg and moves at 5 meters per second. Then we have a motorcycle having a mass of 40 kg moving at 5 meters per second. We are asked to compare the inertia and momentum of each object. For the truck, so our solution for the truck, we know that M is 90 kg, V is 5 meters per second. So that implies that the momentum of the truck, let's use T to represent the truck, is equal to mv, that's mass of the truck times the velocity, which is 90 kg times 5 meters per second. That gives us 450 kilogram meter per second. We have to compare the inertia and the momentum of each object. So for the truck, this is the momentum, 450. Now, take note that the inertia of an object is given by the mass of the object. The inertia of an object is given by the mass of the object. So this implies that the inertia of, let's just use I to represent inertia. The inertia of the truck is 90 kg. So by comparison, we discover that the momentum of the truck is greater than the inertia of the truck as a comparison. Then for the motorcycle, the momentum of the motorcycle is equal to 40 kg times 5 meter per second. That gives us 200 kilogram meter per second. So that the momentum of the truck, of the mass, the momentum of the motorcycle is 200 kilogram meter per second, while the inertia is given by the mass of the motorcycle, which is 40 kg. So by comparison, the momentum of the motorcycle is also greater than the inertia of the motorcycle. So that's our comparison. Let's look at another simple example. We have here a simple problem, very simple problem. An object of mass 100 kg. So our mass is 100 kg. The velocity is 20 meter per second. We are asked to find the momentum. We don't know the momentum of this body, but we know that momentum is simply product of mass and velocity. So this will be 100 kg times 20 meter per second. That gives us 2000 kilogram meter per second as the momentum. So we'll look at a more complex problem and we wrap it up. Here we have a police rifle having a mass of about 30 kilograms, was used to fire a bullet of mass 3 kg at a velocity of 15 meters per second. We have to find the velocity of recoil of the gun. The gun, which is the rifle, is the first object. So when you say find the velocity of recoil of the gun, you're talking about the final velocity for that same gun. So let us bring out all the parameters in the question so that we'll know the exact one to look for. Here, let us treat the rifle as the first object. So we say M1 is 30 kg. It was used to fire a bullet, so it means the bullet is the second object. So we say M2 is 3 kg. And this bullet is moving at a velocity of 15 meters per second. So it implies that V2I V2F is equal to 15 meters per second. For us to find the velocity of recoil of this gun, we'll say that the momentum before is equal to the momentum after. So since we are talking about two objects here, we'll say the sum of their initial momentum will be m1 v1I plus m2 v2I is equal to m1 v1F plus m2 v2F. Now, in this problem, we are looking for the velocity of recoil of the gun. The velocity of recoil of the gun is v1F. That's what we are looking for. But then you check our equation, we have m1, we don't know what is v1I, but we'll get it. We have m2, we don't know what is v2I, but we'll get it. Then we have m1 here, we are to find v1F, we already know v2F and m2. So what is v1I, what is v2I? Now, before this rifle was used to shoot that bullet, we agreed the rifle was in a state of rest. So its initial velocity will be 0. So we say v1I, which is the initial velocity of the first object, which is the rifle, is 0 meters per second. Before the bullet came out of the gun, it was still in a resting state with the gun. So v2I, which is the initial velocity of the bullet, is also 0. So with this point, we can now find v1F. So let's insert every term into the expression. m1 is 30. So say 30. I'll be avoiding the units in my calculation. So just say 30 times v1I is 0. So we say times 0. Close that bracket. Plus m2 is what? 3 kg times v2I is what? 0. So say times 0, close the bracket, equal to, what is m1? 30. What is v1F? That's what we are looking for. So we say v1F plus, what is m2? m2 is 3 kg and v2F is 15. So say times 15. So if we evaluate, this will be 0 plus 0 is equal to 30 times v1F plus 15 times 3 is 45. So we say 45. Of course, we can then say 30 v1F is equal to minus 45. If it crosses the equality sign, it becomes negative. So v1F will now be minus 45 divided by 30. That gives us negative 1.5 meter per second. So the velocity of recoil of the gun is 1 minus 1.5 meter per second. What is the essence of this negative sign? The minus sign, that's the negative sign, indicates that the velocity and the momentum of the rifle are in the negative x direction, that is in the direction opposite to that of the bullet. So I'll just write that here. And let me type that. So I'll say that the minus sign indicates that the velocity and momentum of the rifle are in the opposite direction of the bullet. If they were to be in the same direction, then it will have been positive. But since they're in opposite direction, it is negative. So we are going to come to the end of this presentation. In our next lecture, we're going to give more detailed problems involving momentum calculations. Then we'll now look at the different types of collision. That will be done in the next lecture. Remember to press the subscribe button for more notifications when new videos are dropped. Thank you.